Hello students, I hope all of you are doing well. We have communicated regarding numerical differentiation and numerical integration via our email, and I am happy to see that most of you have submitted the assignments. And if you still have any doubt regarding numerical differentiation and integration, you can email me anytime and I will clear your doubt. Now we will move on to the next part of the unit, where we will be discussing about numerical solutions of ordinary differential equations. If you recall, in your Maths 2 course, you have studied about ordinary differential equations and various techniques to solve ordinary differential equations. For example, the method of separation of variables, method of substitutions, and many others. And you could find out the exact solution for an ordinary differential equations of any order. I hope you remember that. But there are certain situations where it is not possible to find out exact solutions analytically, and in such a situation we go for numerical methods. And I will try to give you an example of such a situation in our assignment problem, and for now you take my word for it, and we will be talking about how to get numerical solutions for ordinary differential equations. Now there are different ways to get a numerical solutions. We can either get a series solution, or we can either generate a series of values of x and y's using various methods. So if you there are different methods to generate a numerical solution. Now in this lecture we'll begin with the method of Taylor, that is how to get series solution using Taylor series. And and in the subsequent lectures we'll be discussing about Picard's methods and Euler's method, Runge-Kutta methods, and so on. Now to describe the underlying idea and underlying concepts, we'll be considering a general first order differential equation. Remember, the theory that we are going to develop using this first order differential equation as a prototype can be used for other higher order differential equations also. As you will see in our subsequent lectures, that any higher order differential equation can be written as a first order system of equation, and then the methods that we are going to use here can be extended to those system of equations. Now let us begin with this general first order differential equation. Look at this differential equation. dy dx is equal to f of xy. This f of xy can be any function which can either be a linear function or a non-linear function. Now we will also be given an additional initial condition here, that is, at a particular point will be specified what will be the solution. That means if you have your solution as yx, then what will be the solution at x is equal to x naught, that will be given to us. This kind of conditions are known as initial conditions. I hope you remember this boundary condition concepts from your Maths 2 courses. If not, please go through them again and clear those doubts. Now let us start with Taylor series solution. Now if you remember in our earlier classes, while talking about root finding methods, or if you remember numerical differentiation, we have talked about Taylor series a lot. We have used Taylor series a lot. Now the underlying idea here is to write down the Taylor series expansion for yx near the point, about the point x is equal to x naught, the point that is at which our functional value is given, and then that series is used to approximate the exact solution. Now let me begin with let me illustrate the method. How can one get a solution? So let me go to the next page. Now see, in this page also we have written the differential equation again. Now dy dx I have written as y dash, that is dy dx y dash is equal to dy dx, and that is equal to some function of x and y. Now as I said, the main idea is to write down or expand yx about the do you know why not dash, why not double dash, why not triple dash, and so on. If you know all these terms, then you are done, then you have your solution, right? So see, why not dash is already there in our equation. This differential equation is given as y dash is equal to fa of function of x and y. Now if I want to find out why not dash, so obviously it will be very easy if I evaluate the function at x naught and y naught. Now I already have my y naught dash that is directly available from the differential equation. Now let us see how can we get the second order derivatives at x is equal to x naught, right? Now remember, all the derivatives that we are going to find out are evaluated at the given point x is equal to x naught. Now what will be y naught double dash? Say, look at this expression. Here it is already written. Now if your y dash is f function of x and y, what will be y double dash? It will be the derivative of this function f. Now look at this function f. This f here is a function of x and y. So using chain rule, what should be the value? What should be the derivative? You should first differentiate this with respect to x, then plus the another term, that is y. Now y is again a function of x, so you need to differentiate y with respect to x. Let me write down y dash, and the function f that we are differentiating, now it should be differentiated with respect to y. Now this y dash is given as f, so therefore we can write the expression as this: y double dash is equal to f of derivative, partial derivative with respect to x, plus y dash is replaced by this given value f and the partial derivative with respect to y, right? So similarly, once you have your f dash, you can find out y triple dash. What will be y triple dash? Similar, y triple dash will be again f double dash, and that we can find out again using the chain rule that is given here. And consequently, if you successively differentiate, you will get all the higher order derivatives. Now see, once I have y double dash, let me explain it using y double dash: fx plus f at function partial derivative with respect to y. Now what will be y not double dash? Simply evaluated at x naught and y naught. It is also, let me write f naught here, so that you understand that I am evaluating at x naught and y naught, right? Now similarly, you can get all the required values. Now once you have all the required values, you have your answer. Now the question arises, where to truncate this series, like up to how many terms you want to consider. Do you want to consider y up to fourth order derivatives, fifth order derivatives, and or do you want to include all the higher order derivatives? Now this is a question that you can resolve, right? Like it depends on how close you want your approximate solution to the exact solution. That means if you want an accuracy of 7 decimal places, 8 decimal places, and so on, based on that you can decide, right? Now uh, so once you truncate, obviously certain terms are going to get be removed from the series now, and that series, that the resulting solution that you get after truncating up to certain terms, let me say I truncate up to y naught double dash, I only take the series including y naught double dash terms, and all the terms considering y naught double triple dash and so on higher order derivatives I exclude. So this is my approximate solution. What was the exact solution? Yx. I do. What will be y double dash? Tell me. So this will be ddx of x will be 1 minus y square. Y square will be 2y y dash, right? Because chain rule, you differentiate it with respect to y, that will give you 2y, and then differentiate y with respect to x, that will give you y dash. So you have this expression for y double dash. See, all right. Now your derivative, second order derivative, is free from x. That means we remember, see, let me write it. X naught was given to be 0, y naught y naught is 1, and y naught dash we just have found out, minus 1. Now if you want to find out y double dash at x naught, that is y naught double dash, if you want to find out, then 1 minus 2 y naught, y naught is 1, 2 into 1, y naught dash is minus 1. So 2 into 1 into minus 1, minus 2 into minus, that means you are going to get plus 2 and plus 1, that is going to give you plus 3. See, that is the value they have calculated here. I hope that similarly you can differentiate and find out all the higher order derivatives. Now see, once you have found out all these values, then you simply plug in into this series and you get your Taylor series solution as this particular expression. Now see, in our question it was asked that find out y at 0.1. So to do that we can simply plug in x equal to 0.1 And remember, we were asked to find out solution that was correct up to 4 decimal places. Now in this case, if you want to find out solution that is correct up to 4 decimal places, we can discard these terms, all the terms, higher order terms, starting from x raised to the power 5, and we can take only this as our approximate solution and plug in x equal to 0.1 to get this as our solution. I hope you understood how to solve a differential equation of this kind using Taylor series solution. Now let me go and talk about an equation that is of higher order, that is not of first order. So to do that, let us look at this particular example, that is y double dash minus xy dash minus y equal to 0. Now see, this equation is second order equation, and therefore you will need two conditions, and those are given to you. See, y at 0 is 1 and y dash at 0 is 0. Now see, you need to identify directly what are given. So I hope that you by now you clearly see that your x naught is given 0, y naught is 1, and this is your y naught dash. So y naught dash is 0. All right. Again, these are the three informations that you are given. Now all you need to find out is y naught double dash, y naught triple dash, all the higher order terms, right? So let us see how we can find out from the given differential equation. Now see, as we did in our earlier case, look at this equation. If I write this equation as y double dash equal to x y dash plus y, then I can directly find out y naught double dash, that will be x, all values at x naught and y naught. Now what is y naught dash? You already know it is 0. What is y naught? That is again 1. So your y naught double dash will be equal to 1 because x naught is 0. Similarly, once we found out, so see now what are the values that we have? We have y naught, we have y naught dash, we have y naught dash, we have y naught double dash. Now all we need to do is we need to find out y naught triple dash, y naught fourth order, and all the higher order derivatives. That we can do it easily as we did in our last example. I hope you can see this expression that we have differentiated with respect to x again. So this is the expression that we are going to wind up with. Then again you substitute x naught, y naught dash, y naught double dash to get y naught triple dash, and consequently all the values you can find out. So and in this way, once you find out all the values and write